The last algorithm we analyze is the OMP. You might wonder why we switched the presentation between the thresholding and the OMP. The reason is that when moving to the noisy case, OMP's analysis is slightly more complex, as you will shortly see. Many of the steps we are about to present follow the ones practiced in the noiseless case, and also the ones we just presented for the thresholding. Therefore, we will allow ourselves to shorten some portions of the description. We start by posing the following condition for the success of the first OMP step. As before, we will develop proper bounds for these two terms and then extract condition on S accordingly. The upper bound of the right-hand side is easy, as it follows exactly what we just did with the thresholding algorithm. The left-hand side term is to be lower bounded. Observe that this time it is a 1 that multiplies b. Thus, the first element in the summation turns out to be x max. Proceeding as before, we break the absolute value into several expressions and upper bound the ones with the minus sign. This leads us to this final expression, which should not surprise you. It is now time to introduce the two bounds to each other, requiring a strict inequality between them. Few algebraic steps that you can easily verify, and we get this lovely condition on S. Remember that this condition guarantees the success of the OMP first step. So the first round of the OMP is successful under this assumption on S, and this implies that an atom from within the support will be chosen. The next steps are to update the solution and then update the residual accordingly to be b minus some coefficient multiplying the chosen atom. As we move to the next step of the OMP, observe that with this update, the obtained residual is the weighted average of the S original atoms, just as B was. This is great, because it implies that with the very same condition, we could guarantee the success of the next round of the OMP. However, there is one delicate difficulty here. The new condition should be posed with x max that refers to the new coefficients in the residual summation. So how do we resolve this? To our aid comes the following claim about the residual during the OMP iterations. It states that as long as this residual is built of the original S atoms plus the original noise, then the maximal entry in these coefficients cannot be lower than the original X mean. The proof of this statement is rather easy. As OMP progresses and chooses atom only from the true support, the residual vector RK does look like the expression shown above. Here is an interesting observation. In this summation, the coefficients of the atoms that have not been chosen yet remain as they were originally. Thus, the maximal entry cannot be smaller than the original X mean, just as claimed. Therefore, instead of using this condition for guaranteeing success, let's worsen the condition and require this alternative one in which X mean replaces X max. This is a worse condition, and as such it covers in it the original one. However, more importantly, this condition now guarantees the success of every step of the OMP, not just the first one. We have this condition as a guarantee for the success of every step of the OMP. This means that after exactly S steps, OMP will recover exactly the support of X naught. What happens after S steps? It is not hard to convince yourself that the residual norm will be epsilon and below. This means that after S steps, OMP stops with a perfect recovery of the support. We summarize our findings with the following theorem. Our goal is to approximate the solution of P0 epsilon, in which P is A times X naught plus noise of norm epsilon, and X naught is a sparse vector. Then under the following condition, OMP is guaranteed to recover the exact X naught support and do so in S steps. Let's try to summarize the kind of theoretical results we have gathered so far. We studied the basis pursuit, the OMP, and the thresholding algorithms. In exploring their performance, we consider two different and worthy goals: a tendency to provide stability and the ability to recover the exact support of X naught. Observe that we did not prove that basis pursuit recovers the support of X naught, and instead suggested a stability result. As for the OMP and the thresholding, both provide a perfect recovery of the support, and thus their stability error is the oracle's one. Comparing the conditions for success is hard, but we do see that basis pursuit is not sensitive to X mean or X max. while the greedy methods do show such sensitivities. So with this table, it would be hard to predict which of these methods is likely to perform better. The common practice is that thresholding is inferior, while the other two, OMP and basis pursuit, are roughly comparable.